All right, so I did get a couple questions this morning. First is starting with the Newman projection for the problem on the discussion board this week for organic. And also kind of like just rehashing or going back over the CIP rules for assigning RS notation. So just a reminder of the discussion board question this week. Let me bring up, of course, you can log in. Courses, organic, and collaboration. So we're looking at the Newman projection along this. So way you can look at this, we can do this by building the model, or we can do this by inferring from the structure. So what I'm going to do is I'm going to build the model for you first. So our model, up, down, up, down, up, down, need one more. So this is your starting molecule. And what we're doing is we're looking from this bond to this bond. So what we're going to do, we want this to be the front one. So we take it and we turn it to the left. We're going to get, take it, go to the left. We're going to have a hydrogen going down, this methyl group going down, and then we're going to have this CH3 growing up. And from behind, we've got hydrogen going up, methyl group going up to the right, and then we've got the CH2 group. So if you look at the drawings on the website, the only one that looks like this bottom drawing here is number 3. Now, how could we do this if we weren't, if we didn't have the model? Well, we're going to be turning it right. So everything that is out of the board is going to be on the right side in our drawing. Everything that is into the board, everything that's dashed is going to be into the board. Now, by convention, anything up and down is part of the backbone. So we've got that part of the backbone going up. So there's my CH3, CH3. My methyl group is going down to the right. And then we're always going to have these at 180 degrees that represent looking down into the tetrahedral carbon with one bond going into the back. So our other one there is our hydrogen. Now, if we look out at this one, this one is anti-relative to this one, so this is going to be our CH2, CH3. Our methyl group is up and to the right. And since in the Newman projections, everything that's wedged has to be on the same side, everything that's dashed has to be on the same side, we know that these two are going to have to be on the same side of the drawing because they're both wedged. And our third group is going to be our hydrogen. So how do we do the CIP rules? So the CIP rules, there are the true CIP rules and the ones we're going to use for alkanes. And the ones we're going to use for alkanes, they are still the true CIP rules, but they're kind of more of a consequence of the CIP rules. So let's look at carbon-3. Now the CIP rules say that the elements with the highest atomic weight take higher priority. And we use atomic weights and atomic numbers because atomic number, let's say you have an isotope. Isotopes can give rise to chirality. We can actually measure it, and you'll talk about it when you go take organic 2. There's some compounds like ketones that will actually substitute their hydrogens with deuterium under the right conditions. So you can actually get these, like, you can create chiral compounds using isotopic labeling. So we don't do it by atomic number, we do it by atomic weight because the atomic weight is kind of intrinsic to the given atom that's doing it. So hydrogen, therefore, 1H is always the lowest priority because there's nothing of higher weight. So around this atom, we've got 3 things, or 4 things: hydrogen, a methyl, this group, and this group. So what we look at first is the element that is bound to the carbon that we're looking at. So if we draw this structure here, we've got a carbon, carbon, a carbon, a hydrogen going back, and a carbon going forward. So the hydrogen here is the lowest priority. It's number 4, but the other elements out here are all carbons. They all weigh the same thing. We haven't specified an isotope, so we have to treat them as the same element. So what we do next by the CIP rules is we look at what they're bound to. So this carbon is bound to a carbon, hydrogen, and a carbon. And this carbon is bound to a carbon, a hydrogen, and a carbon. So if we look at these in terms of weights, we see that, bound to a carbon, carbon, hydrogen, carbon, carbon, hydrogen, there's really no difference. So now we have to start going further out. Now we can go left or right side. For this one, it doesn't matter because we're just getting 3 hydrogens. But if you look at this one, this carbon has 3 hydrogens. This carbon has 2 hydrogens, and another carbon coming off of it. And so since we've got that extra carbon here, whereas this is 6 hydrogens, this is 5 hydrogens and a carbon, this branch here ends up taking the highest priority. So this would be 2. Now the carbon that shot off down here was surrounded by hydrogens. These are all bound to carbons. So this ends up making it the 3rd priority. Yeah. And because of this one's got carbon and carbon's bound to it, it ends up being 2nd priority. So this is kind of a lot, especially with alkanes. As alkanes begin to branch off longer and longer chains, you can still get chiral compounds, but you can get nightmare compounds where you really have to get far out into the molecule before you can really start assigning the actual rank of the group. So example of this, cyclohexane. So these are 2 chiral centers. This is not a Miso complex because you don't see the mirror image. But let's say we want to rank this as RS. Well, this is bound to a carbon with 3 hydrogens. And yeah, let's be extra cruel. No, that's correct. This is a carbon and 2 hydrogens. This is a carbon and 2 hydrogens. And you have to keep working your way around the chain until you finally find a branch. So a corollary of the CIP rules is that it's a higher rank if it branches first. And it's a lower rank if it terminates first. So let's say I gave you some unwieldy compound. Now, this is a chiral compound. How do you assign the RS, the R or the S to this carbon and this carbon? Well, we do what we did before. We've got a hydrogen, that's going to be the lowest group. Our methyl group here terminates in hydrogen, so it's going to be the next highest. But here you have to start counting your way out. So you go 1, 2, 3, 4, and you finally don't see anything until you get the first point of difference of the 5th carbon. So instead of having to constantly go through this, what's bound to this? What's bound to this? What's bound to this? What we do for an alkane is we're going to say, okay, which one branches or ends first? So this one branches first. So this direction here will end up being the highest priority, and this leads to the 2nd priority because it's definitely higher than the methyl group and the hydrogen. For this carbon here, we can take the same approach. We've got our hydrogen, which is our lowest priority, our methyl group, which will end up being 3. Now we start counting out. So 1, 2, 3. This one terminates first, so it's the lower priority. This makes it 2, it makes this direction 1. So the CIP rules definitely do it by atomic weight. They don't do it by first branch, but if you work out enough of these, what you begin to pick up on is this pattern. So if you have just carbon and hydrogen, we're not talking about like alkyl halides. Anything with heteroatoms, so the oxygen, nitrogen, sulfur, chlorine, bromine, iodine, fluorine, those are a lot easier to work with because it becomes really apparent where the first point of difference is. But for something like an alkane, where you just have nothing but carbon and hydrogen, we have a corollary of the CIP rules, which if you work out the CIP rules over and over and over again for these alkanes, you will come to the same conclusion. If it branches first, it's higher rank. If it ends first, it's lower rank. All right, so that was one question. And then the Fischer projections for number 5. Oh, lab assignments, and then 6 and 7. So, number 5. Number 3 in the lab is Chirality R and Antimer S. So let me bring up the lab manual. So I'm not remembering what these are off the top of my head. Okay, so for question 3, you're just told to draw 2-butanol. So you can draw it any way you want to. So we're not specifying stereochemistry. What we're doing is we won't put the wedge and the dash in there, even though you can identify it as a chiral center. So in this case, we don't specify the R or the S configuration. And then the nice thing is that you know that there's going to be 2. And you know that they have to be enantiomers because they're mirror images of it. That's where this wedge and dash flip comes from. So we only have to figure out the chirality of one, and then we can start tweezing out the chirality. And then the chirality of this one's just the opposite. So if we do this one, that's going to put our OH group on the left and a hydrogen on the right. And we can start tweezing out the RS. So hydrogen's the lowest, oxygen's the highest. And then just using the rules we talked about, this terminates first, so this will be 3, and this will be 2. So from the Fischer projection, if we swap the lowest priority group with what's cross-referenced, in this case it's the OH, the H, CH3, branch CH3, and then we just erase the lowest priority group and look at the direction it goes. So we have 1, 2, 3. This is clockwise, so this is going to be the R conformation, and this is going to be the S conformation. Or not conformation, S stereoisomer, and R stereoisomer. All right. So for number 5, the Fischer projections. So when you work it out, these are the 3 possible stereoisomers. So to draw the Fischer projection for rings, start with a box. And then you draw a line for each carbon. So 1, 2, 3, 4, 5, 6. Now, traditionally the way I draw them is I take the ring and I turn it to the left. And so everything that is a wedge is going to appear on the left side of the Fischer projection. Everything that is a dash appears on the right side. And we get to arbitrarily pick our first carbon, so I like to pick the one that's got the first branch on it. So we have a CH3, H, HH. Since they're both wedged, CH3, H, and the rest of these are going to be hydrogens. For this one, the wedge is on the left, dash is on the right. Now this one, we got the CH3 on the right. And then the wedge here, CH3 on the left. So honestly, I find Fischer projections for rings to be a lot easier. Now, in principle, what you could do is you could turn the other way. You could turn it's on its left side, and all your wedges end up being on the right, so all your dashes end up being on the left. It's just going to change the order. Fischer projection start with the OH. No, it's just going to be, instead of having the wedge one, you're just going to be starting with the dash one. So the question got asked in the previous example, if you start with the OH on the right group, it just corresponds to the bottom one I had drawn, which was the OH group and the dash. And honestly, if you don't want to work with a line bond drawing, the Fischer projection is the same thing. So you can start with a Fischer projection where it's just OH on the right, and as long as you correctly identify it as the S conformation, the mirror image of that just has the OH on the left, and because it's the mirror image, it's going to be the R conformation. So in terms of drawing the, identifying the enantiomer and the stereoisomer, this is where the line bond drawing is going to be a lot more helpful. Here you see the mirror image, so this ends up being Miso. There is no mirror plane here, so since this is a mirror image of this, you flipped all the wedges and dashes. These ends up being enantiomers. So for question 6, I'm just going to do a few of these. I'm not going to do the full iteration. So you've got a cyclopentane group and you've got 2 methyl groups. And you can put the 2 methyl groups wherever you want. So we can put them on the same one, then we can do the 1,2 and 1,3 conformations. So to draw this, same idea. So go to CH3, CH3, and the rest of these are just hydrogens. I'm going to leave them blank just because I don't feel like drawing them out. Now for this one, the question is, do we have stereocenters? And the answer is we do. If you look at both of these end up being stereocenters. So if we draw one where they're both wedged, there's your mirror plane. And so there's only one stereoisomer for this, and it's that. If we do the dashed, we don't have that mirror plane. So we're definitely going to have an enantiomer, and the enantiomer is going to be this with all the wedges and dashes flipped. So this is going to be one conformation. If we make this a dash and this a wedge, this is the other conformation. That's your enantiomer pair. To draw it, CH3, H, CH3, and the rest of these are hydrogens. Same thing's going to hold for here. If we do both of these wedged, there's a mirror plane running through here. There's only one version of that, and it ends up with CH3 groups both on the same side. If we do wedge and dash, we're going to see one on one side and one on the other. Now 7 is the full-on nightmare scenario. So there are no Miso complexes for 7, but it's all going to take the same approach. So we're just going to look at 2. This is another one where you're given 2 groups, in this case a methyl group and an OH group. This ends up being achiral because it has a ring attached to both sides. If you tried to assign priorities, you'd find that you were constantly you couldn't assign priority because it looks the same both ways. So in terms of your Fischer projection, it doesn't really matter which one you put on the left and the right, because ultimately this is an achiral compound and your Fischer projections are not meant to really be analyzing achiral compounds. So this, or with the CH3 group switch, OH group to CH3 group switched, it's the same answer. If we move them, this is where we begin to see the chirality pop up. Let's put an OH group on the top and a CH3 group on the right. So we draw a ring. 6. So we have OH, CH3. The rest of these are hydrogens. Since this is chiral, the enantiomer has everything flipped. And the same thing is going to be true of the Fischer projection. So it's going to work the same way the Fischer projections have been working before, that if we want to switch the chiralities, we just swap horizontally the H and the OH, the H and the CH3, and for the enantiomers, we should switch them entirely. And so these would be enantiomers, and then your other option is having them alternate. All right, so I've gotten a question from actually my Chem 1 students about doing so I'll finish this question up. So is it chiral or achiral when you look at this one? So if we look at this group here, we have an OH group up to the right, we have a hydrogen, and then if we look to the right, we don't have a CH2 group, we have a CH3 group. If we look here, it's a CH2 group that bridges it. So this one's chiral because you've got 4 different groups, the OH, the H, and then you got a carbon coming off that has a methyl group attached, and then you have a carbon coming off here that doesn't have anything attached to it. If we looked at this one, it's the same story. We have a hydrogen, a CH3 group, a CH2 branch coming around here, and then this carbon here has an OH group. So when they're not on the same carbons, these are definitely chiral centers, because if you look left and right along the ring, clockwise and counterclockwise, you don't encounter the same thing. So for a ring, what you're looking at is if you start working your way around the ring, and see if I can build you a ring really quick. So let's say the blue carbon here is when I'm questioning if it's a chiral center. So what I do for the ring is I start looking around the ring. So when I have the 1-1, they're both on the same group. When I work my way around, these are both CH2, CH2, CH2. I don't see a point of difference. But now they're on different points. So let's keep looking at the blue carbon. I've got a hydrogen, a CH3, and if I go right from your perspective, here's a CH2, but if I go the other way, I end up seeing a carbon that's not a CH2 group, but a CH with a group hanging off of it. And then, remember, even if they're both CH3, so let's say I do the same thing. So for CH3, I've got, we'll collapse it down to cyclopentane. So this is my carbon of interest. I've got a hydrogen coming out. I've got a methyl group. Now if I look around the ring, if you're going counterclockwise, the first group you encounter is a CH with the CH hanging off of it, and if you go the other way, you have a CH2. So there's your point of difference. You actually have 4 groups here. This one group, if I were to hang it off, looks like it's got a methyl group hanging off a carbon, off the first carbon. If I look at it the other way, this group looks like it's got a methyl group hanging off the last carbon. So they're definitely not the same groups. So to figure out if it's different on a ring, all right, so my software crashed midstream. It looks like, based on the lag I'm seeing in the video, check it one more time, that, where did you stop streaming? Yep, yeah, you crashed really early. Okay, so a lot of stuff got lost. So the last question I saw and I was trying to answer was about atomic configuration, but I'll go ahead and answer the question here about chirality and rings. So when you look at something like cyclopentane, and you want to know if these carbons are chiral, you're not really, so let's say we want to identify this carbon as if it's chiral or not. It doesn't matter that these are both methyl groups. They're not connected to the same carbon. What matters is what's branching off of this carbon here. So if we take our cyclopentane and we'll make this blue one here our top carbon, we've got 4 groups hanging off it. We've got the hydrogen, the CH3, and then as far as the ring goes, we start to figure out if the ring is truly, if the ring is really creating chirality or not. What I like to do is I start at the carbon I'm looking at and I take it and I move out to the adjacent carbons and I say, are these carbons the same? So this is a CH2, This is a CH3, they're not, therefore it's different on both sides. If I had the 1,3, so I have hydrogen methyl, I move out, these are both CH2s, nothing has changed, but then if I come down here, this one's got a CH2 and this one's got a CH3. But if I take something like an alcohol, so let's say I do problem 6, which has the OH group in it. Is this carbon chiral if I put an OH group here? So I've got an OH and I got a CH2 group. And now if I look at the ring, if I go to the first carbon, they're both CH2. And if I go to the next carbon out, they're both CH2. And then I'm back together on the other side of the ring. So this is definitely achiral because if I look left or right, I just see a mirror image. I don't see anything different. But the instant I move a group off to the side, I no longer have that mirror image. I can't sit back and say that it looks the same left and right. Now, this is not the same thing as Miso. Miso, you have chiral centers, but they are related by a mirror plane. So this compound here, as drawn, looks Miso, but we would actually need to go through and look at the wedge dash drawings. So if I look at this, this is a Miso complex. And the thing about Miso complexes is they have to have chiral centers. This is what makes them different from just an achiral molecule. Miso compounds act achiral, but they actually have chiral centers. And so yes, these two methyl groups are the same, but if you look at the RS symmetry of these, they're mirror images. So one's an R, one's an S. So the chiral centers are there, they just cancel each other out in terms of the optical activity. Whereas if I take the trans version, there's no mirror plane here, and you don't create or destroy chiral centers by like changing them both wedge or both dash. You create or destroy chiral centers, you may have to make sure that carbon has at least two groups that are the same hanging off of it. All right, the question I answered, but apparently it never actually went out, was about electron configuration. About electron configuration of cations and anions. So to do this, let's start out by talking about just the neutral compound, neutral atom. In this case, we'll look at carbon. So carbon starts out with 6 electrons. It's got the 2 1s electrons, the 2 2s, and 2 p electrons. And so our orbital affinity diagram looks like this, and our electron configuration is 1s2, 2s2, 2p2. Now, what the charge is going to tell us is the number of protons relative to the number of electrons. So if we have a positive oxidation state, we have lost electrons because electrons have negative charges. The reason we have that positive electron is because we've lost the the reason we have a positive atom is because we've lost electrons. Conversely, if we have an anion, we have more electrons than we have protons, and so we have a negative charge because we have those excessive negative charges. So for carbon plus 2, we just eliminate 2 electrons, and we start out with the highest energy electron. So this would put us at 2p0. If we had carbon plus 4, we would lose an additional 2 electrons. So we'd have 2s0, 2p0. Conversely, if we went to carbon -4. So carbon's going to start out with its 6 electrons. This -4 means that there's 4 additional electrons. So we go 1, 2, 3, 4. So we have 1s0, 1s2, 2s2, 2p6. So the only thing that these charges tell you is how many electrons you're going to lose. So you start with the base configuration, and then you add or subtract electrons depending on the charge. If it's got a positive charge, you lose that many electrons. If it has a negative charge, you gain that many electrons. All right. Okay, so for anyone who checks back through this recording and is really curious why there's this weird sudden gap in the video, it looks like at about the about the 23-minute mark, the software crashed on me. So that's why there's suddenly this gap. Hopefully, those of you who need to get your question answered get answered. Looks like I answered most of the questions up to that point. All right, so I've got the video up. I'm gonna respond to a whole bunch of emails I'm suddenly getting right now. So if you have questions, post in the chat. Again, these are office hours. They are not lectures or lessons, so I have nothing prepared for this. It's open to anyone, so you don't necessarily have to be my student taking my courses. I'm free to answer any questions about chemistry. All right. All right, doesn't really see anybody in the live stream, so I'm going to go ahead and sign off. Thanks to those of you who were able to make it today. Again, if you have any questions, please feel free to either show up or email them in advance. I will see a lot of you in person tomorrow, and then we have live streams Thursday and Friday.